for the invitation. So I'm from UC Davis, which is only 1 hour and a half up in the north. So we're very welcome everyone in the industry or in academia to come to visit us and give a talk there. So today I'm mostly going to talk about building dialogue systems, so trying to connect the two sessions together from less supervision to dialogue modeling. So before we go dive deeper into what we do, I wanted to give you a look into 5 years ago. We see this ACL submissions. You wanted to try to find where the dialogue section. It doesn't even deserve as its own bullet point. So the highlights of all these major submissions are machine translation, document categorization, tagging, trunking, and parsing. But if you look at the recent 2019 ACL, we really see dialogue is really coming up and to be a really popular application. So it's almost as popular as machine translation, which is very surprising. So people may ask you the question, why? Why dialogue is such in 5 years, it's boosted up all the submissions, all people suddenly looking at dialogues. So yes, one of the things we can think about is, so this is one of the workshops that we had, which has 400 people, which is way beyond what we expected. So because one of the things is we have real world applications that really build on dialogues. So for example, we talk about Siri, we talk about Google, Google Now, and Cortana, all these popular personal assistants. But we also wanted to talk about is there are other applications in real world in other areas that really were cause for dialogue applications, such as entertainment, education, and healthcare. So for example, in entertainment, we can create a more targeted advertisement. We can create social bots to provide companionship for elderly patients. In education, we can provide training for second language learning, for leadership, all these kind of interactive training. So we can also build teaching assistant for online education platforms. In terms of healthcare, we have been collaborations on building social, we would call it virtual agents to screen for mental disorders. Or you can even do rehabilitations for some of the diseases like aphasia or dementia. You can also persuade people to do physical exercise to help them to have a better life. So the most popular ones that you have been using right now are mostly on customer services when it comes to task-oriented systems. So providing information and providing actions and in return. So we have been seeing more and more we call it marketing or what we also call it non-collaborative dialogues, trying to persuade people to do things, trying to negotiate with other people, trying to battle against scammers and attackers on telemarketing. So there are all these interesting applications, but we're not really limited in terms of only having the voice output or text output. We're really looking at multiple modalities in terms of output as well. If we have vision, then we have basically animated human beings on the screen. So we can build games, movies for that. And then when it comes to physical manipulations, then we become robots. So now dialogue system is a robot. So the natural communication between a human and a robot can really enable a lot of different tasks, such as search, rescue, nursing, and all types of physical manipulation plus human collaboration. So, but we are still facing a lot of challenges at the moment. That's why all these great projects I have been talking about are still academic projects. We haven't seen it in everyday life. So one of the biggest challenges what we see is history or context tracking. So what makes a conversation is because it has multiple turns. So that differentiates conversation with question and answering. So how do you track efficiently all the context, condense the context efficiently, is one major big problem. We know all current neural networks can only track a limited context. A bird only tracks 500 tokens. But in human conversations, we can go on for hours. How do we condense this information? How do we build models to basically have a better representation of the history is very essential. And the second one is not enough data. So we all know, like in conversations, when we look at data points, one data point really requires two people talking together, or one human, one machine talking together. So collecting one data point costs a lot of time and money. So having like millions of conversations on specific tasks is not possible. So people may say, maybe you can just try to fund the data on internet. You can look at Twitter, you can look at Reddit. But the problem is, in internet world, so people are really talking in internet language. It's really different from how we talk in face-to-face or how we talk with personal assistants. And also, it's super noisy. It's really difficult to utilize them. So we have been making some progress in terms of cleaning these data for pre-training, but it's not going to be used for target domain training. So how do we solve this no data problem? So basically, we're going to design models to try to sort of transfer learning or unsupervised or semi-supervised learning, try to bridge it. Another task specific to dialogue is we may talk about like task-oriented system. So there's always a task here. Different tasks really brings out all the variety in language and policy and interaction. So for example, I try to persuade you to do donation. It's gonna be vastly different from me talking to a therapist about me having depression. So how do we actually account for all these different domains and trying to build a model that is generalizable to all domains? It's not really possible. But we're still trying to work out ways to build some certain models that are generalizable to a specific targets, for example, information request task. The last one, and I think it's the most difficult one, is that we're actually having a moving target. So a lot of times when we look at vision or NLP tasks, we're doing a lot of batch testing. So basically, once we collect a data set, we're just gonna improve models on that data set. But building dialogue system is about talking to humans. So what is a good dialogue system? It has to be evaluated by the end user. So basically, you're trying to know human is similar to each other. So we have to make sure that the system is able to adapt to different users. So it's really difficult. So in real world testing, if you're talking to this human, the system says something slightly different from the ground truth. And then the human is gonna reply very different things compared to the ground truth. So if you wanted to collect a ground truth data set, it's gonna look like it exponentially grow in terms of the tree structure. So it's impossible to have a static data set for you to train and test on. So this is the one biggest problem. No good evaluation, automated evaluation metric is really possible for dialogue training. So we have been looking at a lot of things like how to do user simulations, how do you try to do budgeted training and policy to mitigate that as well. So today, mostly I'm gonna focus on the not enough data, and it's something we did. So learning to reduce supervision mostly is we talking about reduce the number of data points, reduce the level of detailed labeling we need, or reduce the number of data points that we have labels. So, but it also is about increase in terms of something that we can get for free, like multimodal information. When you talk to a system, some information you're collecting for free, like acoustic information from your voice. Context information, for example, who you are, your profile information is visible to some of the personal assistants. So for example, who you are, how old you are, what is the previous context of your information. So today I mostly talk about one thing that I think is gonna be really applicable in deployed systems, which is what is the trade-off between how many data points you have and how many detailed annotations we need. So, so a little bit of basics so we can recap everything. So existing dialogue frameworks usually looks like a modular framework. So you have a natural language understanding, then dialogues tracking, and then policy planning, then natural language generation. But the another popular framework is called end-to-end framework, which is mostly popular within the academia. So we're trying to see if we can combine them together to actually build a dialogue framework that is applicable not only to research, but also for deployment. So a little bit of basic, what is natural language understanding, right? So you have some user utterance, and you wanted to basically decode it into a distributed semantic representation. So something like we constrain ourselves in the restaurant search domain, or say, I need something that is in east part of the town. So that's your input, and you want to translate that into the user intent, which is inform, and the slot information, which is east. So basically, we're trying to do this kind of translation from the natural language to a scripted language. So previously, a lot of other people have been doing classification or sequential tagging on that too. Then once that you have the understanding outputs, you're gonna do dialog state tracking. So which basically is you have the dialog history, you want it to condense all the information that is necessary for the next step planning for the system. For example, you have this kind of context. I'm looking for a moderate price range Italian restaurant. The system say De Luca's Cucina, and a bar is a modern European restaurant in the center. And then you would say, I need something that's in the east part of town. So we wanted to basically combine these kind of raw text together to translate them into a condensed form, which is inform, price equals to moderate, location equals to east. So a lot of things that we have been using as like a sequential classification or sequence generation for these type of converting from natural text to condensed state, dialog state. Once that we have the dialog state, the next thing is about planning. So you know all the information from the previous previous dialog, then you wanted to decide what the system should do. So basically you want to map the dialog state to the system action and some slots. So here, one example is I have the actions inform, price, moderate, location equals to east, just what we got from the state previously. Then we're basically gonna look for the database and find the information. And the next thing we're gonna let the system to is provide the restaurant name, price, and address. So this is basically a policy planning. So you can really think about supervised learning or reinforcement learning. So basically, you wanted to have this type of mapping from state to system action. Once you have the system action, now you wanted to translate it into natural language so everybody can understand you. So from provided restaurant name, price, address into Curry Prince is moderate price and located at 452 New Market Road. So it's also a sequence generation problem. So when you look at a dialog research paper, it's not only we're not solving one task, we're actually solving 4 tasks. So it could be a different combination of these 4 tasks together in a paper. So what are the problems with these modular framework? First, it's difficult to update. If you update your natural language understanding model, everything in the downstream is gonna be affected. You have to update them equally, but it's really difficult to do that all at the same time. So there are heavy expert involvement, so we have to hire researchers to design every module carefully, tune them carefully, and also we have to have a lot of manual annotation because we need the semantic representations, we need the state tracking results. So that's why the natural thing is, why don't we just do end-to-end? We blend everything together. We have the user utterance, we wanted to just get the system utterance. So is that actually possible? One possible problem with these type of framework, it's really difficult to perform error analysis. You don't know if the system is doing something wrong. You don't know what's going on. You don't know if it's the understanding having a problem because it's system can't understand the user utterance, or it's the planning that has a problem because the system has a glitch in database search. So it's really difficult to identify what are the errors. And then after these data-driven methods, one of the drawbacks is you need thousands of dialogues to train one single information request task. So there's no perfect framework in this. So what we're trying to propose is trying to combine the 2 frames together, trying to solve some of these problems, but still we're gonna next time we're gonna improve even better. But now, at least we can say it's a model that is end-to-end trainable. So we're gonna use encoder-decoder model. And then we wanted to inject supervision from every module individually. So what you can see is something like that. For example, if you only have the supervision from the natural language generation part, then basically that's your end-to-end framework. But now, we wanted to add an extra decoder in NLU, DST, and DPL, so that you can feed this supervision from these decoders individually as well during the training. So one of the special case of our framework MOS is the previous work called TSCP, which has 1 encoder and 2 decoders. So one decodes dialog state, the other decodes natural language generation, basically the system response. So our model basically say one instantiation is if we have all supervisions from every model. So instead of having 2, we have 4 decoders. So we have one decoder that decodes natural language understanding, so basically the system side intent and thoughts. And then one decoder decodes dialog state. And the third one decodes dialog policy, basically the system's intent and slot. Finally, the system's utterance from NLG. And a previously modular framework is trying to basically populate these information only through the results. We're trying to populate the information through hidden states. So everything is connected. For example, the information we got from the NLU, we're basically going through hidden state to feed it to the dialog state tracking. The same thing goes to dialog policy planning and natural language generation. So what we really see is a end-to-end trainable framework. That the encoder is basically, you have the previous, what we call a belief span, which is a concatenation between the output of a dialog state and dialog policy. Then the previous response of the system plus the current response of the user. And then you have the natural language understanding component that takes the hidden state from the encoder, previously the HE, and then you're trying to decode not only the output MT, but also a hidden state MT tilde that you're gonna propagate to the next decoder. So right now we're at the decoder for dialog state. So it's the same idea. You're not only gonna output the ST, but also have a hidden state you're gonna propagate to the next module, which is dialog policy planning. So the same thing goes on until you get into the final language generation. So everything is connected through hidden states. And finally, we're basically going to train it in a multi-task setting. So you combine all the cross-entropy loss of each module together as your major loss. So one thing that we also wanted to point out is our framework is super flexible. It can take different type of annotation. So even if you have one data set, so part of them only have the NLU annotation, part of them only have the dialog state annotation, part of them only have no annotation, but only the natural language sentenced by the system. We can still combine them together because our framework is basically propagating through hidden states. If you don't have that part of the supervision, you just don't do gradient update on that particular model for that particular data point. So everything can be blended together. So it's flexible in terms of whatever data you gather, you can basically update the model. So it's in a very flexible mode. It's very friendly to deployable system. So here is basically what we wanted to point it out in terms of the trade-off between the number of data points you have and the level of detail of training annotations you have. So we talked about TSCP, basically it doesn't have annotation for natural language understanding and dialogue planning, while MASL basically has extra annotation. But what we can see is if we have more level of annotation, only 60% of the data we can outperform the TSCP using 100% of data. But the problem is it's always a trade-off. You can't get everything in one model. There is always a trade-off. So it's a design process for the engineer to think about whether you want to collect more data or you want to do more annotation. A lot of times there is no perfect model. There's only one model that suits your specific setting. So for example, if you're opening up a new product, you have customer service on that particular product, but you just don't have enough data for training. Then what you want to do is you want to annotate more detailed semantics within the utterance from the user and the system. If you have more data, you don't have to annotate all these kind of detailed semantics. You just use data, the dialog states that you annotated to train a model. So we also try to, one thing we wanted to point it out is, for example, you only have 60% that annotated with all these kind of detailed annotation, but you have 40% that it has no annotation at all. You can still combine them together in the MOS framework, and you can improve in terms of success F1 as well. So the framework is also very nice, friendly to error analysis and in terms of updates. For example, this is an example. I say, I'm looking for an expensive restaurant in the South. And the ground truth system utterance is, hi, we have Mexican, Italian, Indian, Chinese. Do you have any preferences? So the mouse basically learns to ask what type of food are you interested in south part of town, so which is also correct compared to the ground truth. And I also produce the dialog output, which is ask for food type. So I know exactly what the system is trying to do on each step. But TSCP, the previous result that does not have the annotation for dialog act on the system side, can only generate an utterance. For example, curry garden is inexpensive Indian restaurant in the south part of town. Basically, according to the ground truth, he is making an error. But we don't really know which part of the system is wrong. Is it because the understanding is going off, or is the dialog tracking going off? But MOS gives you some like intermediate feedback to know what's going on. So if you do error analysis, then you know like your understanding is making an error. What you do in real life is you collect more data that targeting this understanding error, and then you feed it back, the annotated data, to your MOS, and then you can update your model. So MOS gives you the better error analysis, also give you a better procedure in updating your model with more training data, targeted training data. So the MOS framework basically is saying like we can do a little bit better in terms of updating your model. We do better in terms of performing error analysis. We still have some of the expert involvement because you still need to design the end-to-end framework. But we don't have to design 4 models. We just need to design 1 model. We also, like, there is always a trade-off between how much annotations that you want to make and how much dialogues you're going to collect. It's always a design choice that you have to make it yourself. We can only give you some guidelines and some standard data sets. So one of the bigger problems we haven't solved is we can still only do information request tasks, unfortunately. So I have a new talk called Non-Collaborative Dialogues, which is going to talk about some more complex dialogues like persuasion, negotiation, anti-scam, but for another time. Still, like we wanted to focus mostly on these kind of simple customer service tasks. What else can we do if we don't have enough data? So another thing we want to talk about is kind of how to reduce the data point in training a dialogue system. So if you go to an industry and look at their dialogue manager, sometimes you see this, which is what we call a dialogue flow, which is a very deterministic on each step what you're going to do. This one is for getting weather in Delhi and New York. So for just such a simple task, you have like a huge graph. So if the task is more complex, your graph is going to be exponentially big. So it's going to be really costly to build such graph. So what we're trying to do is, can we actually leverage the unlabeled conversations? You have a lot of customer service conversations. Can we explore and construct these type of what we wanted to do in terms of structure automatically? So one thing, simple thing you would think about from Jason's previous work is you're going to use HMMs. They have time series. So you're going to model this kind of structure in time. But however, it doesn't really give you very informative structure. So what we're going to do is we're trying to use the more advanced neural methods, as we all know. So particularly, we chose the variational RNNs. So we're trying to basically reconstruct this conversational structure or this kind of flow graph. So here, the one difference we make is that we have this kind of latent vector. So previously, what we call latent vector is everything that is trying to, you wanted to group them into. So this latent vector in our dialogue situation is the latent dialogue states we want to represent. For example, looking for a restaurant. And then we have the hidden states of RNNs, which is like a standard things you do in neural network. So we changed the previous variational RNN into a discrete state. So basically, we want to make sure that the latent dialogue state we're learning is actually discrete, so we can actually to draw the graph out. So we use Gumbel softmax to convert it from continuous to discrete. We also changed the structure so that it fits the dialogue more. For example, the previous model of the VRNN really uses a hidden state as the prior. Now we're changing using the previous latent state of dialogue act dialogue state to influence the current dialogue state. So now the connection is more direct. So we can learn these kind of interesting flows automatically, which it's not perfect, but it serves the first base for the human to come in to edit it, to have a better, more compliant dialogue flow. So for example, we can learn in the restaurant data set again. People are usually looking for a restaurant. They're asking for the address and the phone. If they got the information, they're very happy. They say, you're welcome, right? But there are some other branches like looking for a restaurant, but didn't find something. They're sorry, there's no match result. Then you go into another state and trying to change your address, change your criteria to find another. So at least these kind of graphs shows you like what's going on in your data. So we can't really, so previously we can't really see these kind of loops inside of HMM, but now we can see these kind of interesting structure. We can also utilize this interesting structure to build actual dialogue systems. So for example, if we use RL to build a hybrid code network, which I'm not gonna elaborate, which is gonna take a while. So basically, our idea is given a dialogue state, we wanted to know what are the action the system should take. So we can utilize the structure we learned as a guidance, which injected into the reward, so that we can actually learn the system much better. Because the structure we learn from human-human conversation, you can think about it as an optimal choice that human are learning. So you wanted the system to learn it as well. So if you add this kind of extra reward, we can basically improve the performance over 30%. So the takeaway for this particular one is unsupervised learning methods can work for a certain degree, and it can help you to discover these structure from unlabeled data sets. It can also help you to train your RL-based dialogue systems. Another different work from ACL we're gonna just gloss over is we really see in personal assistants, we have so many skills. I've got thousands and many. Look at this is 100 best Alexa skill. Of course, I heard there was close to 5,000 skills. So we have all these kind of skills which are individual domains. So the problem is, if we want to build a new system in a different domain, is there a possibility to leverage all these 5,000 domains? These domains may have a lot of training data. Maybe we can use close-by domains instead of invent our own, collect our own training data. So this really comes into our work is trying to use meta learning to combine information from close-by domains, could be restaurant, weather, to improve a low-resource domain, such as a hotel booking. So they're all in the booking area, but they are different in terms of different entities they track. But we can still leverage the sentence structures from all the other domains to help us to build this low-resource hotel domain. So I'm not going to go into details. If you're interested, you can look into our recent ACL paper. Basically, we wanted to combine this kind of meta learning in the dialogue setting. So we want to do two-state update. So the first step is individual domain, you do a gradient descent. Then finally, you're adding every domains together to get a loss function, then you update the joined loss. So then basically you're saying the model that I'm training is similar to every domain that we have, but they're not on the average, but they have individual differences in the updates as well. So they are far away from each individual domain, then it might be more closer to the target domain. Finally, I want to conclude in terms of, we say we wanted to train systems with less data, but we also wanted to include more free information. So we are talking about multitask learning, unsupervised learning, semi-supervised learning, or transfer learning. But we also wanted to think about what are the things we can add to the current model. For example, multi-model information, such as vision or acoustic. For example, recently we had a paper on using sentiment as an immediate, what we call an indirect feedback. So that during the conversation, you know, oh, if the user is not happy, I'm probably not doing a good job. So that could be a reward function for your reinforcement learning. So we also can consider context information. Context is everything. For example, who the user is, whether it's demographic information, personality, previous purchase history. Everything could be really helpful for your model to actually require less data to learn more targeted model. Okay, I wanted to conclude my task and take more questions.
Thanks, Zhou. We have time for like 1 or 2 questions.
More questions.
I can't tell. So I have a question.
Okay, sure.
So what kind of data sets have you been using for your work? Because you've exposed a lot of the challenges. And
Yeah, so the data set, collecting good data set is always a problem. So we have been using, for example, some standard task-oriented data set, like a multi-WAS and Cambridge Restaurant 676. We also collected our own data set. So our recent data set is a persuasion data set, which 2 Turkers are playing the game of trying to persuade people to do donation. But we put in terms of like money into their own calculation, so they're actually not doing only simple role playing. They're like your money in stake when they're doing this kind of targeted donation task.
And they play the role of agent and customer in that framework?
So mostly we're, in terms of academia research, we're working on data that are role play. You know, mostly is because of privacy issues. You can't really get customer service data from companies.
Right. Okay, great. Thank you very much. Let's thank the speaker
thank you.
again. Thank you.